Sorry, your name again? Nicolas. We have Nicolas from Lagrange Labs, and you're going to be talking about verifiable data for the new internet, which I'm excited about.
Yes. Hi everyone. So this is going to be relaxed talk, so feel free to interrupt me with any questions. There's the first high general part about what we do at Lagrange. I have some slides for more technicals, or people that want to ask technical questions. So we can go either directions. So yeah, I'm Nicolas. I'm leading the engineering at Lagrange about our ZK core processor. And this is a fancy title, but basically we are building a ZK core processor to process historical data on chain. And we're going to see in these next minutes what's all about. So this is some high-level slides again. We are right now. Lagrange is a decentralized prover network powered by eigenlayers. So it's an AVS. We have many different provers running Coinbase, OKX, 8 layers, doing this. And it's been running live since mid-April. It's our first V0 version. And we're planning to release a V1 with much more features. We're going to talk about a bit later down the line next month. So basically, what it's all about is we are building think of a verifiable SQL VM that you can access on your smart contract. So basically, you can query any large amount of historical data. So think about mapping the balance of user across the last 1,000 blocks or 1,000,000 blocks or whatever. You can do rewards through computation, things like this. We can go over the use cases afterwards. And it's really about large-scale computation. Instead of just proving some historical slot, like a dozen or 50 of them, you can prove over millions of range. And so basically we are doing two things. We are indexing the data from the blockchain. We are taking the data, which is complicated with KCHAC and NPT and all this stuff, really a non-ZK friendly kind of data structure. We are putting in our own data structure, which is very much ZK friendly. And then we enable queries on top of it. So with this, then you can query the blockchain very efficiently for large-scale computation. Think of it for those who know what MapReduce is, it's really trying to build a verifiable MapReduce as well. So basically, that's a high-level view of the network, how it works. We have this notion of a gateway, which actually received this is the entry point for developers, basically. So this is our gateway, and this is the network. Okay, so the gateway is just simply a middleman between the blockchain, where we are actually asking to index some contract and asking some queries over some contract, and the proving network, which is actually generating the proof. Okay, and it does a lot of things, which we can talk a lot bit down the line. And the second part is actually the prover network, where it's decentralized using eigenlayer right now. And so it's using economical security just for liveness. So we're still relying on the full security of ZK for completeness, for security. But for liveness, we are actually asking our prover to have some stake in it. So if they don't answer with the proof in certain time, they can be slashed and so on and so on. But actually, slashing is not it's a complicated topic. But that's basically the major two components in our network so far. So far, so good. Please interrupt with any question if you have. Again, like I said before, Lagrange work in two separate stages. So the first one is, I have a contract, I want Lagrange to start indexing. It's like if you were putting your data into a SQL table. You create a table and you start updating the table, inserting data to the table. That's exactly the same feature here, except that well, your data comes from your contract, so you need to decide which variables you want us to index. Like if you have a mapping of address user balances, things like this, if you have a price, if we have a standard deviation, whatever, you can name it. We can index this for you, and we will automatically index at every block. So at every block, we're going to look at your storage, put it into the database just for you. Okay? That's the first stage. That's what we call pre-processing here. The second stage is the query. So now that we have put this data into our nice database, which is ZK friendly, small technical parenthesis, it's very, right now our design is very simple. It's the Merkle tree with Poseidon, thinking this very, very straightforward things to do on a proof, on ZK proof. Then we can actually query it. And querying for us is super let's say, fast and cheap because we are actually tuning the database for it to be very cheap in ZK world, let's say. Notice that our database is made such that we can query, such we can insert data insert efficiently and very fast, in a very fast way, and query as well in a parallel way. So we can scale horizontally. Let's say the more machine we have, the more compute we have, so the faster, let's say, and the more large-scale computation we can go. Actually, we can go into detail why this is horizontally scalable, but just this is one of the main criteria for designing our database here. So how does it work with privacy again? So you have the blockchain. It gives you a block every 12 seconds for if, or every 3 seconds for Teams if you want to do this. So what does it contain, the blockchain? So for a specific contract, you will have what we call a storage trie. Okay, so if a storage trie contains all the data of the contract. Okay, it contains the balances of the address, the balances of the user, etc., etc. What we do is we transform it into this provable database. Okay, which is here the color only the color changes, but actually even the shape of the database changes. It's not the same shape as the blockchain because the blockchain is MPT3 with 16 children. There are many rules. There are LLP to SketchAct. All of this we get rid of. We prove we correctly extract this data from the blockchain, but we insert it into a much more simple and friendly, ZK-friendly database. That's what we are doing at every block. Okay, so every block we're still appending to our own provable database. And then we have the query phase. So again, like I said, provable MapReduce or provable VM SQL if you want. So think of it like this is like showing just a very simple example about computing the sum of all the balancing of a user across the last 4 blocks. So imagine these leaves contain the balances of a single user across the last 4 blocks. Then what you do is just you do it parallel. So you aggregate these two and you do the sum, these two and you do the sum, and then these two and you do the sum. So you can do layer by layers in parallel. And this is one of the things we can do horizontally scalable because if you put 1,000 values, then you can compute all these values in parallel and aggregate in parallel. I'm going to get into more detail as well if people want afterwards. I have some side forks. And at the end, you get the proof, and we send back this proof to the smart contract that asks it, so for a specific user, everything like this, and then the smart contract just receives an array of results, depending on the query he submitted, and then it can do whatever it wants with it, depending on the actual computation. So far, so good. Let's go. So right now I'm going to show you what is currently in V0. Again, we have a V1 coming up next month, which should be completely different because in V1 you'll be able to actually write your own SQL query using our frontend. You're gonna really, we are trying to be exactly offering the same Web2 experience as in what we can do in Web2 for writing SQL queries and getting back the results. So, like for example, just let's, I'm going to go quickly over this one, but basically, for the solidity contracts, then we can index mappings, we can index arrays, and things like this. Here it's a special case for mappings because of EVM issues. Let's say we cannot know the length of the mapping. So if you want us to prove that we've looked at all the mapping data, we need to do these kind of things. I'm going to go a bit quickly over this because it's not very so relevant for today. And this is just a single line. We say our contract register this the storage contract over this lot, and that's all it takes. Okay, basically. So I'm putting aside the whole economical aspect as well. Basically, it's just a simple call to our database, to our contracts that is going to trigger an event, and so our offstage system, the gateway that I showed you before, will be able to pick up and start indexing the contract database over this specific steps. So imagine this lot is really the user balances of USDC. And then the query database, well, right now again is for V0, where we kind of hard-coded some specific queries just to showcase and start something simple with this technology. In V1, we're going to be able to let the user express their own queries in SQL. This is just for V0, so basically here we just request, give me all the NFT IDs from this order, from this block, start block, to end block, and give me the offset, because if there is like, if think of it like you return an SQL table, so you can have a very large value, so if you offset, we limit by 5 right now, so you offset, you can select exactly which portion of the result you want to see on chain, because on chain we cannot put 1,000 of results obviously, so we have to do this pagination, but it's roughly what you would do anyway in Web2 world, except usually in Web 2 world you can allow for thousands of results. Here for blockchain, let's say scalability issues, we don't want to put thousands of results on transaction, but this is really same similar thing. Yeah, that's about it. So this is a very quick slide again, high-level slide about how the database works. Like the criteria for designing the database. We want it to be ZK-friendly, obviously, because we're offering a ZK proof that we both extracted the data correctly and we both computed over this data. Okay, this is really important to prove both the indexing and the querying parts together. And we want it to be horizontally scalable because, let's say, the major effort in ZK world and ZK proof world focus on having one big prover that can take a lot of things at the same time and produce a single proof. We focus differently. We kind of follow the MapReduce paradigm where we, instead of bringing all the data to one proof and actually running the prover with a single big data and get one proof at the end, we actually bring the small proof to a small subset of data, and then we aggregate these proofs together. So it's really like we don't want big proof. We want fast proof which can recurse between themselves together. Yeah. And one very important property for us is efficiently updatable. So for this, we rely on the research done at Lagrange about which is called rate proof and record trees, where we actually only pay between one block and the other. So for example, imagine we are indexing the balances of all USDC holders. Okay, so between one block and the others, we don't expect a lot of changes in the mapping, maybe tens, hundreds, 1,000 at most, and we only pay because the USDC holders like millions of them. And we only pay for the updates as well. So we don't need to prove millions of entries at each block. We only pay logarithmically from the number of updates. So there's like 3 updates, we pay 3 times log n, basically, roughly speaking. And this enables a huge scalability for us because that means we can update, we can still index the whole storage of the whole mapping at every block, and still paying a very small price between each block. And our assumption is that the entropy between blocks is low, so it's very fast for us to update actually. And we don't really need to prove everything from scratch. We are keeping the old proof and using them for the new block as well. And we can get into more detail afterwards as well, happy to. But this is really a key property for us that allows us to take this blockchain data and put it first in our blockchain. If we didn't have this property, we will have to do like many others are doing and just proving directly and querying at the same time, because we don't want to be indexing millions of entries at each block. It's way too much costly, way too much slower. So this is not something we can do. And thanks to this, we are able to put it in our own database and be able to run fast queries of it. Right. So that's like the major slide if you have to pick up to one thing. About the whole system, how it works roughly. So here you can see that there's blockchain 1 and blockchain 2. That's an important piece of information here because we can index a contract on L1 and answer queries on any L2s, for example. And it's not a bridge because everything relies on the ZK proof security, so mathematical foundations, let's say. Because we are still anchoring a proof with respect to the blockchain 1 hash, block header hash. Okay, so as long as in blockchain 2 you still get the block header hash from blockchain 1, then you can verify a proof. And the transition from blockchain 1 to blockchain 2 is fully secure. There's no optimistic or whatever. Again, the optimistic is only for the ZK proven network, just for the liveness. So how does it go? Here you have the developer smart contract, you register a contract with one, okay, and then it's called this on our own smart contract, then our Lagrange ZK gateway picks up this event and start indexing. There's a whole notion of the scraper here is actually listening for the blockchain, for listening all the updates between each block to the storage slot that are changing during each block. And then we are creating this database. And then you can send a query if you want, and then we can send back the query on blockchain 1, of course. But you can also do it on blockchain 2. Here, you can also send a query with respect to blockchain 1 and get the results on blockchain 2 as well.
Sorry, so you said that blockchain 2 needs to have the kind of like header hash of blockchain 1?
If the query refers to a contract on blockchain 1, yes. Yeah. But you can also index a contract, just indexing the contract on another blockchain. We're not focused on one blockchain. That's one thing. So there's two aspects. There's like the the bridging aspect of the queries,
Yeah.
and also the fact that we support different chains. As long as it's EVM compatible, we are like no aspect.
But you need, so for example, you could get because a layer 1 will have the kind of latest state of the layer 2, you can keep those in sync, or like, is to keep state in sync the main reason that you would want to have this connection, or does that question make sense?
No, it's mostly mainly for cost. For example, right now our main use case is cost because querying on L1 is actually expensive. We need to verify your gross 16 proof, maybe it's like 400k gas, something like this. So usually you want something fast for querying and doing rewards. It's much more cheaper to do it on the L2. Even for rewarding some users, you don't want to pay huge gas cost on L1. So that's also one of the main reasons we started to do this, because otherwise it's difficult to test out and try to hack around things. It just costs you too much. Okay.
I was wondering whether it was something about, for example, some kind of governance smart contract on the layer 1 to be able to like trigger it in a state if something happens on the L2.
I think we don't, Lagrange, the cryptography is not meant to be like a fully general bridge. It's really meant to be querying another contract on any other blockchain and get the result there. So if the DAO, for example, governance DAO wants to query something on blockchain 2, it could, and get back the result there as well. There's no problem about this. But I think the distinction between fully general bridge and ZK cluster is like to define more. But anything is possible in this area. Asking for a query on the one blockchain to the other. Yeah, so far so good on this slide. Because this is the main slide. If you have to take away one thing today, this is about it. So this is again the high-level slides. Well, I just said to you, we launched in April, and this called Euclid. We're going to test our next release next month. We're going to be able to actually run SQL queries. And this is just some big numbers to show that it's running. We're generating a lot of proof every day. And again, I mentioned a lot of proof because we're not doing big proof, we're doing many, many small proof that we get together. So this is why these numbers are very high as well. But we've been indexing since mid-April every block on L1 ever since. And I've received a lot of queries on Base. We are deploying on Base, Optimism, OPStack, Mental, Frax, and others are running soon. And so these are just two slides about kind of some use cases that we are thinking about and that we're actually trying to engage. And we actually get some good collaboration ongoing about this. So the first one, we just tried our technologies. We registered the Pudgy NFT contract. And Pudgy NFT contract is the famous NFT collection. Well, you can very easily with Lagrange prove the duration they held a specific NFT. For example, if you say, hey, if you held any NFT Pudgy contract for more than the last 1,000 blocks, then we can get you a reward or anything like this, or we can expand what the offer that Pudgy Collections wants to offer to its user base. So that's exactly the same flow that I showed you before. Pudgy NFT is on L1, so we index the contract every block, and then on L2, any L2, you can query this contract and get the rewards to the NFT users. And same for the reward pool contracts. So this is a really exciting use case because there's a lot of rewards schemes, let's say, mostly based on Uniswap V3, for example. Most of people are just copy-pasting Hover's contract and SushiSwap as well. But basically, if you can basically look at the ERC20 contract and track all the balances of each user at every block, and then you can actually do the average or do the sum with respect to the total supply at each block, and then that means you get a notion of, let's say, the participants' activities in the LP pool. And from this, then you can actually derive this final value on the very large scale, millions of slots if you want, millions of blocks, and then you can actually get the query, get the results, and then be able to reward as well the user. And this is already what's happening today, but many of the solutions are actually off-chain and completely centralized, and sometimes completely wrong as well. And you have to depend on certain API to always be available. The user have to connect to this API first and then submit a transaction. Like, there's plenty of intermediate steps that are making this harder, they say, to be deployed at scale and in a fully automated way. And so this is like the fully on-chain, let's say, version of it, where you just, every user, when they want to get the reward, they just query Lagrange, and they get back the proof, and they automatically get the reward from the smart contract that gives out the reward. Again, the logic of what we are doing here is just computing the actual final value, where the logic of the smart contract that is deciding how much reward should I give to each user depends on this value. We're not like going fully to the end, but most of the last logic is really super easy to say. If you have the average of 10, then you get 10 new tokens. That's like basically for the main two case studies where like go in collaboration with Refer5 on this kind of stuff. And I think that's basically my last high-level slide when I got this. Again, we have a Discord, feel free to join. We'll be happy to talk about anything there. We have our own Day 1 next month, which is going to be very exciting because, again, you're going to be able to write the real SQL queries and index your own contract as well. Right now, we kind of still permission for many things because it involves a lot of resources, so we can't allow anyone to run anything. But we're getting more of this open in the next coming month. So that's about it for the high-level slides. If you guys are interested, I have some more technical slides to go over what is exactly the technique we're using and things like this. But at this point, I want to stop and ask if any of you guys have any questions about how does it work or like the use cases or anything like this. Yeah, please. Yeah.
So, will you post the slides or will the talks be recorded somewhere?
Sorry.
Will you post the slides somewhere or will the talks be recorded somewhere?
The talks is recorded right here.
Okay, that's good.
We can post the slide as well. I'll see with you maybe about posting the slides somewhere.
Yeah, that's fine.
But yeah, we can post the slide.
There will be a recording as well.
Yep, it's fine.
Maybe this isn't the upcoming slides, but you said you do many proofs. So is that like you take one query and you split different parts of it across many provers, or just kind of each query goes to a different prover? Like how do you do all that separation and aggregation?
I think I should go to the next slide then too.
Yeah, please.
So basically, to enable this kind of technology we're doing at Lagrange, we need two basic tools. The first one is based on the record trees, the research done at Lagrange. So this is like a simplified way to represent it, but let's imagine we have a regular record tree, right? So we have the leaves at the bottom, and we do the hashing between nodes and the hashing at the root, right? So far so good. Usually, the naive way of proving membership of some values inside this tree would be to take all the roots. If you want to prove membership of all the values, you take all the tree and you do the membership verification inside the tree, right? The problem is that now the computation is of n, and you have to redo it each time, even if 3 changes to another value, then you have to redo the whole thing. So that's not good for us. So how does it work? Now, imagine now there's an updated value, right? This is exactly the problem I mentioned here. Now you have to redo the whole thing and still computation is O of n. And we don't want this because, again, between blocks, there's going to be only a few values that change. So we don't want to recompute millions of entries just because of a few values that change. So what we do is actually, we compute, instead of computing one big proof over the whole member tree, we compute one proof per node. We can batch things as well, but this is like a simplified version. So this is a small proof that takes the value of this node and exposes its hash. Okay, same for 3, same for 2, same for 1. And we can do this in parallel. Okay? Once we have this proof, then we can move to the next layer. So once we have the proof for 3 and 3 for 4, then we create another proof that verifies these two proofs here. Okay, it rigorously verifies inside with these two proofs, and it combines the hashes together. And same, it exposes the new hashes now. And so you're basically recursively constructing your tree via proof regression. Okay? And at the end, you get the roots proof, which exposes the root hash. And basically, that's the main trick here. Like the whole thing about Lagrange is really residing in, like the core thing is really residing in this thing. That we can compute in parallel. So here, if we have 4 provers, we can run 4 proofs at the same time and go layer by layers. Okay. Now, what happens is the value change. Well, it's very easy the value change because if imagine 3 was brown before, now it's turned to blue. Then I just recompute this proof, and this proof. I don't touch this one because they're exactly the same. They didn't change at all. So I don't need to recompute the O of n. I just need to recompute block and number of proofs now. And that's what we are doing between blocks. So if only a few users change, then we only recompute the new path that changed here. That's really one of the key tricks that we use everywhere. So we use this on MPT trees, on the storage slots of the contract. We use this internally for our own database, and we can even use this for queries as well, because when we construct queries, we're actually reconstructing the tree, but we can, that's not too much, get into too much detail right now. So that's the parallelization part of Lagrange. The second tool that we need is, the problem is like, what we are indexing is actually on an MPT trie. So it's like very complex. For those who know, it's like using, for those who don't know, it's using a complex hash function getjack and RLP encoding, and like you can have 16 children at some point. You got like between a variable number of children actually. You have 3 different types of node, the leaf, the branch, the extension. Like, it's really a complex beast, and proving this in ZK is really not something we want to do often. So we have to do it once to prove that we really extracted the right value from the right contract, on the right chain, on the right blockchain, block header. But we only want to do it once, and then we turn it to our own database. Okay. The problem is how do we do the equivalence between what is on the MPT tree and our new database? Because we don't want to compute the hash, the same hash that the MPT tree is exposed to. But that's the goal of removing this complexity. So, and so, how do we do this? Well, we kind of, that's like that goal. We want to be able to transfer from MPT to a ZK-friendly tree, which is like this nice record tree. So what we do is actually we use what is called multi-set hashing. It's come from a paper from Sinatedi, and we use it like basically the core idea is just you take. Imagine if it's just a hash where the order of hashing things doesn't matter. So if you put hash of 1, 2, 3, it's exactly the same as hash of 2, 3, 1. And that gives us the ability to hash only the values in the MPT tree and prove that the same hash is included in our record tree. So we do these 2 hashes separately. We can actually prove both trees in parallel, and we don't need to wait for one to the other. And so we prove the MPT tree and our own database tree in parallel. We compute this multi-set hashing, and at the end we show that they are the same. So that means both trees contain the same data. And now that's it. We can only use our own record tree. We are done with the MPT tree. And so combined with the record tree approach, we get both the efficiently updatable and both the translation to our database, and then you can get rid of the tree afterwards. And we do this at every block, of course. So still some work, but the digest translation, we are also keeping it for the MPT tree as well. So we're really doing the same operation in both trees. And so if you want to, this is like putting everything together, but basically once we have this new tree done, then this is like I showed you before for the sum, it's really the same, but for computing the average for the pool, when you look at each proof, it exposes the value and the counter, so the beginning is going to be 1. And so here's like 3 plus 4, and at this level it aggregates the value and aggregates the counter, so 3 plus 4 and 1 plus 1 equals 2. And then you go up to the top, and then you get the average number. And this generalization of computing the query in parallel and with aggregation, think of it as really a MapReduce framework, and MapReduce is able to express SQL computation. So we're actually building some kind of a SQL VM using regression with this kind of design model. How much time do we have? 2 minutes. Yes. Okay, great. And that's about it, actually. I finished.